attention. Hello. All right, so the SI schedule is posted up there. Jess has some announcements to make because there are some changes. The other thing, the Wednesday exam review will be from 7:30 till 9:30, so it'll be 2 full hours, just so you guys know to block that out on your schedules. So Wednesday's exam review will be 7:30 till 9:30. It'll be cumulative, and there will be no practice exam.
Hi guys. Okay, owing to some previous commitments, I will not be teaching an SI session tonight. Srav is covering for me. It's in the same time. It's in the same place at the same time. So if you want to do chemistry, I'm sure Srav would be delighted. Number 2, Alpha Chi Sigma is still having its rush events. There's 1 more week left. Tomorrow is bowling. Thursday is coffee at Arabica. It's free coffee. You should probably go. And Saturday is invite-only Chipotle, free burritos and stuff. So if you're interested in that, that is available for you. Thirdly, congratulations to all of the new Greek women in the room. I'm sure you will all be great assets to whichever organizations you are now a part of. And I think that's all I have to say. The exam review will be in Rockefeller 301.
Those of you whose last names begin with the letters A through C, you will report to room clap 108 on Thursday. Those of you with the last names D through J, to Grace 312. Everybody else in here. I will post this to Blackboard. Not that I'm aware of. Folks, as far as I know, we are the only class scheduled in those 3 rooms. I do understand that Chem 145 or Engineering 145 also has their exam at 11 during the Provost Hour on Thursday. I'm presuming the registrar has not double booked rooms. I will have Brian, my assistant, check on that to make sure. But the way this is set up, we're using 45% of the available seats in each of those 3 rooms. So that means that you will have to sit every other seat. We won't be able to do every other row. Because of that, the people who are in there to answer questions may have to crawl over people to answer questions. If you think you're going to ask questions, be near an aisle, please. Also, let's keep it as we did in the past. Please plan to stay till the end of the hour. We'll collect all the tests at one time so that those who are taking all 60 minutes to do the exam don't have to get distracted because 20% of the people are leaving early. So once you get here, plan to stick around till the end. If you think you're going to finish early, just bring a pillow with you so you can go to sleep. Okay. Same rules as before. I think the administration of the exams went fairly well last fall. We have essentially the same group of people who are proctoring the exams again, so they've been through it before. There's a different person coordinating that group now, but I think they've got it all in hand. Questions about that? Yes? There is no class on Friday, whatever that date is. Yeah, the 8th, right? So take Friday off. I'm contemplating a small change on the syllabus, by the way. That small change is that last day before spring break is notoriously a low attendance day, but it is currently a scheduled class day. It is my intent to have class on that day, although if we had 30% of you here, I'd be surprised. So I may offer you a trade where instead of canceling class on the 29th, besides you can only have class on the 29th once every 4 years anyway, we would have class the 29th and then I'd cancel class on, what is it, the 7th of March, the day before spring break, which is the day your papers due anyway. So you'll all have it done in advance anyway. So But that's the only modification I'm thinking of right now. All right, blank screen. I don't need that anymore, but I do need light. Any other questions? All right. It is a low chalk day. All right. All right. Every year I talk about reaction mechanisms, they seem to be more and more complex. So I want to try to simplify them as much as I can. I say that every year. Hopefully I'll get it right this time. A reaction mechanism is simply a series of steps by which the reaction, the balanced equation that we ultimately see, actually proceeds. Reaction mechanisms can be very simple. They can be very complex. For you guys, they're going to be very simple. I will never ask you to, from a balanced equation, propose a mechanism. That would be far too painful. The reason why is because reaction mechanisms, there are lots of different possibilities. And the challenge, if you study reaction mechanisms, is to come up with a reaction mechanism that is reasonable, that explains your observations, and that you can collect data to prove that it's real. You don't have enough experience or information yet to do that for most reactions. Here's a nice simple reaction. Nitric oxide reacts with oxygen to make nitrogen dioxide. One possible reaction mechanism for any chemical reaction is that it happens exactly the way it's written. In order for this reaction to happen exactly as it's currently written, you'd have to have two nitric oxide molecules interact with one oxygen molecule at the same instant in time and with the proper orientation. And proper orientation simply means if I take an NO gas particle, it has to be oriented NO, and if I orient it ON, it won't work. And if you think about it, you draw the dot picture for NO. Let's see, 5 and 6 is 11. 2, 4, 6, 8. Can't be that. 2, 4, 6, 8, 10, 11. Okay. There's the dot picture for NO. If you assign formal charges, that's 0, 1, 2, 3, 4, 5, and that one's 0. NO is a molecule that its orientation has nothing to do with its formal charge, but that single unpaired electron on that nitrogen makes NO very reactive if the nitrogen bumps into something. If the oxygen bumps into something, nothing happens. Carbon monoxide is a molecule that if a negatively charged particle runs into the carbon, nothing happens. But if a positively charged particle runs into the carbon, it might react. And so orientation has everything to do with geometry. And there's nothing you can do to predict that geometry because these molecules are constantly moving. And so chemical reactions happen 9 times out of 10 by luck. The goal of most chemical processes is to try and control the luck as much as we can to get as much product as possible. Over here, if this happened by a one-step mechanism, it would be called a termolecular reaction. In other words, it's got to have 3 molecules participating, 3 molecules being in the same place at the same time with the right orientation. Termolecular reactions are very, very, very rare. It's highly unlikely that you're going to get 3 molecules in the same place at the same time with the right orientation. A bimolecular reaction, on the other hand, is relatively common. So this is mechanism 1. Mechanism 2 is a 2-step process. The first step is that the 2 NO molecules interact, making an N2O2 molecule. And then that N2O2 molecule interacts with an oxygen molecule to make 2 NO2 molecules. If you add these together, we get an overall reaction that's exactly the same as the one above it. So this is another possible mechanism that we would look at to see if this is what happens when nitric oxide reacts with oxygen. Now you've got to go in and collect some data to find out which of these 2 is correct. Both of these steps, by the way, are bimolecular reactions. There's 2 atoms involved reacting to make products. This N2O2 is a reactive intermediate. In other words, it's something that's produced in one step of the reaction but used up in a later step. So one way to prove that that second mechanism is the real mechanism would be to go and look for N2O2, to somehow measure the concentration of N2O2 as a function of time. And what you would probably see happening is it would look something like that. You'd start with no N2O2, you'd make some, and then it would get used up. And the total reaction would occur as long as there was N2O2 around, but as soon as it was gone, the reaction would have to stop. The other way you would prove this second mechanism is you would measure the rate of the reaction. And what you find out is that that rate for that reaction, two NOs plus O2 to make two N2Os, NO2s, when we do the experiment, we find out that the rate of the reaction is equal to some rate constant K times the concentration of NO squared. And the first day we started talking about reaction kinetics, I told you, you can't take a balanced chemical equation and write a rate law expression. There's an exception. For every step of a reaction mechanism, they're called elementary steps, you can look at the balanced equation and write the rate law expression. So, if this chemical reaction occurred as a one-step mechanism, so in other words, it happened just as it's written up there, 2 NOs plus O2 to give you 2 NO2s, as rare as that might be, the rate for that reaction as it's written would be this one. So if that one-step mechanism was true, you could take the balanced equation, you could write the rate law expression as being the concentration of the reactants raised to their stoichiometric coefficients. In other words, it's second order with respect to NO and first order with respect to O2. But when we do the experiment, we find out this isn't true. That's not the observed rate law. Emma? For this one up here, the one we're still stuck on, the first one up there. That one. It's the one, we're saying that this overall reaction happens in one step. If it happened in one step, that would be the rate law. But that's not what we observe. From the data, I know that the rate of the reaction is equal to this. So that means I have to come up with a rate law, a mechanism, that has that rate law. Well, what's the rate law for the first reaction up there, the first step? It's the rate is equal to the K times the concentration of NO squared. That first step in this two-step process has this rate law. What's the rate for the second reaction? Because it's an elementary reaction, any elementary reaction, you can write a rate law expression just based on the balanced equation. The rate for the second step, because every step in the process has a rate associated with it, is K times the concentration of N2O2 times the concentration of O2. So which one is the one that describes the reaction rate for the overall reaction? If there's two possible rate laws, which one is going to be the one that determines what's going on? The second part of a rate law mechanism, of any reaction mechanism, is that in addition to coming up with a series of steps that equal the net reaction you're talking about, you also want to determine which steps happen fast and which ones happen slow. The analogy is a garden hose. If I take a garden hose that is some diameter, and then I connect that to another garden hose that is a smaller diameter, and then I connect that to a third garden hose that's big again, the rate that I can get water to go through those three segments of hose is going to be solely determined by how fast can it get through there. How quickly it gets done is determined by whatever the slowest step in the process is. If I want to create, well, no, don't do that. Take that one out. Any process that I want to undertake that has a series of steps, the total length of time it will take to complete that entire process will be determined primarily by whichever step is the slowest one. Over here, if this is the reaction mechanism that we're going to say is right, since this step is slow, it will determine how fast I ultimately can make the product that I want. Bless you. So the rate law for this overall reaction based on this mechanism will only be based on this slow step. And the rate for that step is equal to that. As I said, I'll never ask you to take a balanced equation and give me a possible mechanism. There are just too many possible things that could come up. I may give you a mechanism and ask you if it's a valid mechanism for the reaction we've got.
So what if the slow one is the one that has the intermediate,
What if the slow step is the one that has the reaction intermediate in it? A valid reaction rate law can only include concentration of reactants, products, or catalysts. Reaction intermediates can't be part of the mechanism. The reason is because we have no way of measuring the concentration of reactive intermediates. We can go in and measure them and make sure they're there, and we might be able to monitor their concentration as a function of time. But you'll find out you can never measure the actual concentration of it. And since we can't use it in a rate law. Yep. Is there a way of knowing which step in a mechanism is the slowest one? No, there's not. You actually have to go in and test it. And so when people come up with reaction mechanisms, they might propose this very elaborate process of 10 or 11 steps, and they'll say, this is the slow step. How do you know it's the slow step? Because when you write the rate law based on the balanced equation, it gives you a rate law that agrees with the data that you've got. And so the art of creating reaction mechanisms comes down to what's a realistic product that I might make when I react this with this if I stick to bimolecular reactions? And what's the probability that that's going to be a fast or slow process? So it takes practice, it takes intuition to do these things, which is why I'm not going to ask you to do it. The slow step will never involve the intermediate. It can't. So reactive intermediates can never be part of the slow step. Emma?
So if you said you can't derive the rate law equation from a balanced reaction, why were you able to do that in that first equation? And you like you're using balanced equations to formulate rate laws. Like when can you distinguish that?
The only time you can write a rate law equation from a balanced equation is if that balanced equation is an elementary step in a reaction mechanism. The definition of an elementary step in a reaction mechanism is one that you can, by inspection, write the rate law expression. So for any reaction, you can propose that the mechanism is a one-step process. Well, if it's a one-step process, that means I can take the balanced equation and write the rate law expression. But the number, and for some reactions that's true. If I take hydrogen and react it with chlorine to make HCl, it's very possible that the rate law is equal to the concentration of H2 times the concentration of Cl2. That's a perfectly legitimate mechanism because it's bimolecular. H2 and Cl2 are similar single bonded compounds. That would work. Is that what happens with HCl? No, it's not. What happens with HCl is that you get chlorine to fall apart into two chlorine radicals. In other words, you get a chlorine atom with that unpaired electron on there, and then that chlorine radical reacts to form HCl plus a hydrogen radical, radical being an unpaired electron on there. And then the two radicals come together to make HCl again. If I add these 3 steps together, let's see, there's 2 Cl radicals here, there's one here and one here, so they cancel out. There's a hydrogen radical here and there's one here, so they cancel out. So there's a 3-step mechanism that I could have said happens as 1 step. What if it happens as 1 step? All I've got to do is get 2 molecules together in the same place at the same time with the right orientation. That's not so tough. This one, and then you're saying, okay, why does chlorine fall apart? It doesn't unless you put light on it. You add light to chlorine and you can get chlorine molecules to break apart into their atoms. Now those atoms have that unpaired electron. Guess what? They're very, very reactive. So this step is very fast. Guess what? I still have unpaired electrons in here. This step is very fast. This step, however, is the rate determining step. It's the slow step in the process. So if this mechanism is a valid mechanism, the rate for the reaction would simply be K times the concentration of Cl2. If I've got more Cl2, I'm going to make more radicals. It should go faster. Well, that makes sense. If I've got less Cl2, I'm going to make less radicals. It doesn't go as quickly. So I would propose this 3-step mechanism. This is the rate that goes with it because that's the rate of the slow step. And now I have to go prove it. I haven't proved it yet. I've just shown that it's a possible mechanism because the other thing is when I add the steps together, I get the net reaction I want. How would I go about proving this now? A, you'd go and you'd measure the rate as you change the concentration of chlorine. If the rate does indeed increase as you increase the concentration of chlorine and it's first order, in other words, you double the concentration, you double the rate, that supports this mechanism. What if I do the experiment and I change the concentration of hydrogen and I find out it changes the rate too? Then this mechanism's not right. So I have to go back to the drawing board and try again. All right, let's ignore that for a second. We found out that when we doubled the concentration of chlorine, we doubled the rate. We found out when we doubled the concentration of H2, nothing happened. So far, everything about this mechanism looks reasonable. Have I proved it yet? No. What do I have to do to prove it? Now, to prove it, I'm going to go out and I'm going to look for chlorine radicals. It ends up they're very easy to find. Even though they react very quickly, they're relatively easy to find. Anytime you have a single unpaired electron on an atom, you can find that compound easily. They interact with light in a very nice way. So I go and I look for this, and lo and behold, where did it go? I erased it, didn't I? I find out that the concentration of chlorine radicals as a function of time looks like that. Now, think about what I've just done. I've just showed that it's first order with respect to chlorine because when I doubled the concentration of chlorine, I doubled the rate. I showed it 0 order with respect to hydrogen because when I doubled the hydrogen, nothing happened. And I showed that I made chlorine radicals and they disappeared over time. I've now shown that they exist. Have I proved this mechanism? All the data supports this as a possible mechanism. Have I proved it? Only as much as science allows me to prove it. It's completely valid. It supports everything I know without having some other option that does the same thing. Yeah, this is a valid mechanism. Is it the right one? That's a real tough thing to determine, which is why I told you last week that nice simple reaction was responsible for the 3rd Nobel Prize ever. even when you know everything you can about it, it's very difficult to prove an exact mechanism. But it is possible to propose mechanisms that are reasonable. All right. Your book doesn't do much with them. All right. I do need to define one other thing, though. And I can do it with this one. The process of nitrogen reacting with hydrogen to make ammonia can be catalyzed. We can speed up the reaction. We're going to take the energy level diagram, just the book would call it a cartoon, that says, I'm going to start at some amount of energy. I don't know how much energy it is, but I know it's some amount of energy that is equivalent of the energy of 1 mole of nitrogen and 3 moles of hydrogen, whatever that is. This reaction occurs, and as the reaction occurs, the energy is changing. You're breaking nitrogen-nitrogen triple bonds. You're breaking hydrogen-hydrogen single bonds. Remember, that requires an input of energy. And then you're forming NH bonds, 6 of them. That gives off energy. The net process is an exothermic process, so that after some period of time, I'll be at a lower energy than when I started. And when we first introduced these last semester, we said all chemical reactions want to go downhill in energy. That's still going to be true. The problem is, if I've got to break that nitrogen-nitrogen triple bond, and I have to break each one of those hydrogen-hydrogen single bonds before I can make the 6 nitrogen-hydrogen bonds, I have to put some amount of energy in before I can get this reaction to occur. So if we were to follow this as a function of energy, we'd start at some value, we'd start putting energy in so we can start to break all those bonds, and then at some point we'll have put in as much energy as we need to, and then it's straight downhill from there. The reactive intermediate is at that point. Over here, the N2O2 could be found right at the peak of that thing. And so the reason why you can look for it is because it really exists for some period of time. Those chlorine radicals, it takes energy. You put light in, H nu, and you take Cl2 gas and you make 2 chlorine radicals. It takes energy to break that chlorine-chlorine single bond. But then once you're at the top of that thing, even though it's a short-lived process, you could measure what's there. There's another problem with this now, though. When I'm right at the top of that hill, which way am I going to go? To the right or to the left? You have a 50-50 chance of going both ways. Just because you got yourself to that point, there's a 50-50 chance that you're going to go one direction or the other. And so you don't know. That's the beauty and the challenge of chemical reactions. Just because you started the process going, you can't guarantee you'll get products. The grail for most chemists is to make sure that you can get the product you want, even though statistics says you can't. So, I want to speed this reaction up. I'm going to bring out another curve that you've seen several times this year. And that's this energy distribution. Plot the number of particles on the vertical axis and the total energy on the horizontal axis. And we've already said it looks something like that, where temperature is a measure of the average energy. If I raise the temperature, I shift this curve out so it gets longer in the tail on the high energy side over here, but the peak comes down a little bit. But the total area under the curve stays the same if I raise the temperature. What I'll tell you is that we're going to define different parts of this. This is delta H, right? That's the change in energy between products and reactants. This thing right here is the activation energy. It's the amount of energy you need to put in to get over the hill. If you don't put that much energy in, you don't have a chance. You've got to put at least that much energy in. On this curve over here, there's the activation energy. So what does that curve tell you? It tells you that all of these particles right here have enough energy to get over that barrier. So you'll make some product, probably. But everything else doesn't have enough energy. So how do I make more product? The answer is you add a catalyst. What does a catalyst do? A catalyst speeds up a chemical reaction. How does a catalyst speed up a chemical reaction? It changes this curve. If you change the process of going from starting point to ending point by adding something in there, you lower the activation energy. When you lower the activation energy, you've changed the path from products to reactants. You get a faster reaction, because now, if I still have that same distribution of particles, this now we'll call EA star because there's something different about it. Now look at how many particles have enough energy to get over that barrier. If they get over that barrier, what happens? You make product. Excuse me. So the purpose of a catalyst, we always say it's to speed up a chemical reaction. Really, the purpose of a catalyst is to give you an alternate route to get from point A to point B. And the route that you have with the catalyst has a lower barrier to get over, and so you get more product. Now comes the $50,000 question. Does the reaction mechanism depend upon whether there's a catalyst or not? Yes. Why? Because the reaction mechanism is another word for the route. The route from reactants to products is a one-step process where we started right there. And we said that that's not very likely. It has a huge activation energy barrier. What if it's a two-step process? By making it a two-step process, you've now changed the route to get from reactants to products. And so you're more likely to get more products. What if it's a two-step process with a catalyst? The catalyst has to be part of the reaction mechanism. And because it's something that we know we can put into the mechanism, into the reaction, and because we know how much, it can be part of the rate law where the intermediate cannot. So catalysts, and you're going to do it in biology, folks. Our book even does it in biology. Enzyme catalysis. What is an enzyme? It's a substance that acts as a catalyst. What does that catalyst do? It gives you an alternate route from reactants to products. And the beauty of catalysts, and the reason they cost so much, is because while they might get used up in an early step in the mechanism, they're brought back as a product in a later step. So guess what? You dump in a catalyst, and it doesn't go away. You take a little bit of catalyst and dump it in there, and that's enough to last forever. The best catalyst that you all know about is that converter on the underside of your car. You've probably never looked at it, but you have a catalytic converter on the underside of your car. What does it consist of? Rhodium. It's finely divided, ground up rhodium metal. There is currently a huge black market in catalytic converters. There's a story in Newsweek magazine from a couple weeks ago where people are going in, especially on things like Cadillac Escalades because they're so high off the ground, any vehicle that they can get under quickly and easily, and they're just taking a torch and cutting off, or a hacksaw, and cutting off the catalytic converter, dropping it out of there, going to the local salvage yard and selling that catalytic converter. Why? Because even though there's only about 5 grams of rhodium inside that catalytic converter, rhodium currently sells for $1,500 a pound. And so that 5 grams of rhodium is worth about 150 bucks. And you know what they get from the salvage yard? 25, 30 bucks. But how much effort does it take to slide under a car, take a hacksaw, cut it off? You could probably do 4 an hour. You can make 120 bucks an hour doing this. That's the thought process. And you know what? The salvage yards are paying the money. They just hand you the cash. And then what do they do with it? They sell it to a big salvage company who then takes that catalytic converter, cuts it open, pulls out the rhodium, separates it out, and they sell it for $1,500 a pound to a jewelry company. So those of you who drive vehicles that are high off the ground, watch your catalytic converter, because what does it cost for you to replace it? It's about $1,250 to replace your catalytic converter. What reaction does it catalyze? All right, the question is, in your catalytic converter, what does it catalyze? It ends up the catalytic converter is great because it catalyzes more than one reaction. Guess what? That thing over there, nitrogen plus hydrogen to give you ammonia, it's also catalyzed by rhodium. It ends up that the reason why, the mechanism they've discovered for this process, what do you think the rate determining step is? Just looking at this balanced equation, what is the slow step in this reaction? Breaking the nitrogen-nitrogen triple bond. Think about it. It's 900 kilojoules per mole to break a nitrogen-nitrogen triple bond. It's huge. The way that it works is that the nitrogen comes in and knocks itself and connects to the surface of a metal. And once it connects to the surface of the metal, the intermolecular forces of attraction, the intermolecular forces of attraction between the metal surface and the nitrogen atoms is greater than the attractive force between the two nitrogen atoms, so the nitrogen-nitrogen triple bond breaks. Once it breaks, the nitrogen atom reacts with hydrogen very quickly and to make NH. NH reacts with another hydrogen to make NH2. NH2 reacts with another hydrogen to make NH3. And so the slow step is getting the nitrogen onto the metal surface. In this reaction, we take octane. And octane, remember, is just a generic name for gasoline. It's actually C8H18, and there's probably C9H20, and there's probably C6H6. There's all kinds of hydrocarbons in there. When you react them with oxygen, you always, 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 in a combustion reaction, make CO2 and water, unless oxygen is the limiting reactant. And if oxygen is the limiting reactant, you make carbon monoxide. Well, we don't want carbon monoxide coming out of our cars. And so the catalytic converter absorbs the carbon monoxide that is produced, because it will be produced, reacts it with oxygen that is there. It holds on to the carbon monoxide and lets more oxygen in, and reacts it with oxygen to catalytically convert it back to CO2. So the catalytic converter takes carbon monoxide and makes CO2. The other thing it does is it takes nitric oxide, because where does the air come from, or where does the oxygen come from in your car? The air. What does the air consist of? 78% nitrogen. You put nitrogen into a high temperature furnace like your car engine, and what happens to nitrogen when you put it in that high temperature furnace? You break some of the bonds. Now you've got this very reactive nitrogen. Guess what it bonds to? O2. What do you make? NO2. Draw the dot picture for NO2 and you'll find out it has an unpaired electron. Guess what color NO2 is? Reddish brown. You want to see a picture of it? Look a satellite image of LA. That reddish brown haze that floats over LA is NO2 gas. What do you do with NO2 gas? That single electron, it reacts with water. When NO2 reacts with H2O, you get HNO3. So the other thing your catalytic converter does is it takes the NO2, reacts it with oxygen to make it takes nitric oxide and makes N2O. Nitrous oxide comes out. So if you're really, never mind, I won't say that. All right, I will see you on Wednesday.
When did they start using rhodium? I thought they still used platinum.
They use platinum too.
I wondered why rhodium was so expensive.
But rhodium got real expensive real fast.